This lecture covers the first part of Chapter 10, which is on hypothesis testing. So, hypothesis testing is the second part of statistical inference. So, remember that statistical inference concerns the process of inferring results from some sample out to the entire population. And once you've done that, you want to ask about this inference. And there's really two approaches to this. One is to look at how stable the estimate is. And that's really the Chapter 9 approach, where you use confidence intervals and margins of error. The Chapter 10 approach, the hypothesis testing approach, is to approach it a different way, where you're saying, what can I say about the parameter in relationship to other numbers? So that's the first part of Chapter 10. Or other parameters. That's the second part of Chapter 10, which we'll cover in a subsequent video. So just to motivate this, turn to page about 191 in your course packet, and we have a little problem. So McDonald's conducts customer satisfaction surveys and have been doing it for many years. Over this time span, McDonald's has established various norms for what a franchisee should be at if they're doing okay. For example, the service norm is a 2.6. Presumably this is measured on a 3-point scale, although I guess it could be 4-point. So if you do a survey of customers at McDonald's, and if you find that the mean is 2.6, then that particular franchisee's location is a typical one. If they're above a 2.6, then they're doing really well in service. If they're below a 2.6, then there's something wrong, and McDonald's should jump in and fix it. So let's say that McDonald's wishes to test whether or not some new training program will improve the service score. So McDonald's has been very innovative in training their employees. They have a hamburger university out in Oak Brook here. So employees at some particular store, which is known to have a true mean of 2.6, are sent to the new program. After they return to work, McDonald's then goes off and draws a random sample of 100 customers and administers its survey. This survey finds that the sample mean is 2.74, and the standard deviation is 0.8. So the question is, does this new program improve satisfaction? Now, there's a managerial question attached to this. Do we roll out the new service training program? If they do this and it's ineffective, they're wasting their money. The results from this sample suggest that the new thing works, but this is just a sample based on 100 customers. So let's see how we approach this in Chapter 10. What we're going to do in Chapter 10 is state two rival hypotheses. The first one is going to be called the null hypothesis, and it will be denoted by H0. So the 0 means null or not. Statisticians tend to say H naught. So the null hypothesis is that the mean of the new program, so mu is the true mean of the new program, the mean satisfaction level after people have been trained for this new approach. So the null is that this mean is still 2.6. So let's just call that the business as usual hypothesis. The alternative I'm going to state is that mu is now in fact bigger than 2.6. The new program therefore works better. This H1 is called the alternative hypothesis. It's also called the research hypothesis. Another term that you want to know is what this 2.6 is called. So 2.6 has a number of different names, sometimes called the reference value. That's what Siegel calls it. Test value is another term that you might see. So whenever you see that, they mean that number that's sitting in both the null and alternative. By the way, you always stick the equal sign in the null, and then you stick either a greater than, a less than, or a not equals into the alternative. So what we'd like to do is evaluate whether it's possible that the data that we've observed, so we've observed a mean of 2.74 out of a sample of 100, could be possible if this null hypothesis is true. That's the basic strategy we're going to follow. Before we get to analyzing it, let's think about what could happen. So, in truth, either H0 is true, meaning the new program is no better than the old, so the new program really doesn't work any better, or H0 is false, where the new program is better. Now we have to make a decision. Either we're going to accept H0 and roll out the new program, or we will reject H0, conclude that it's no better than the old, and therefore not roll it out. Now, if H0 is true, and we decide not to roll it out, we've done the right thing. Likewise, if H0 is false, and we reject H0, roll it out, we've done the right thing. However, there are two ways that we can make a mistake. Let's start with the lower left box down here. So if H0 is indeed true, so this program really is no better than the old, but we decide to roll it out, we've committed a type 1 error. Now this is also called a false positive error. In the medical literature, it's called a false alarm in the engineering field. And usually we'll use the letter alpha to indicate the probability that we make one of these false positive errors. Let's talk about the other type of error. So the other type of error is where the new program is in fact better, but we decide not to roll it out, and therefore we've missed an opportunity. This is going to be called a type 2 error, and sometimes you'll hear it referred to as a false negative. The probability of making one of those is usually referred to as beta. So with that said, let's go back and examine the McDonald's data. So the usual solution to this is as follows. We're going to start by, statisticians call it conditioning on the null. So we're going to say, assume that H0 is true. So assume that the true mean is 2.6. So why don't we just go draw that for a second. Here is the distribution of x bar. If the true mean is 2.6 and the mean of the sampling distribution is also 2.6. So we'll just assume H0 is true, which means that mu is 2.6, and so the mean of the sampling distribution is also 2.6. Now, we want to evaluate how strong our evidence is against the null. So let's go over to this picture, and I'm going to sketch in 2.74. 2.74. So all of this cooks down to us evaluating the area in this tail. Now, before we actually find that area in the tail, so that's just a chapter 8 question, let's think a little bit about what the area of that tail is going to tell us. So we'll do a little thought experiment. Let's say, for the sake of argument, that we find the area in this tail and it works out to be 0.00001. Okay, now if that were the case, what would that tell us? Well, it would say that if 2.6 were the mean, then the chance that we would observe a 2.74 or bigger essentially can't happen. All right, so if that were the case, we would reject this being the mean. In fact, I'm going to go draw an alternative. Here's the alternative distribution, which is out here someplace. And all right, so if the area in that tail is minuscule, we would say that this can't be the mean. The true mean must be out here for this red distribution. All right, so let's continue with our thought experiment now. And let's say instead that we find the area of this tail, and the area in the tail works out to be pretty big, like 0.4. Now if that's the case, what we would say is that it's entirely plausible that we would observe a value like 2.74 if 2.6 were the mean. And therefore we would not be able to reject that the mean is 2.6. We wouldn't say that 2.6 is the mean, we would just say that it's a possibility. So that's our little thought experiment. Let's go back to the course packet and actually find the area in that tail. Well, we're now back into a chapter 8 problem. The standard error is going to be 0.8 over root 100. So what's the chance of us observing an x bar greater than 2.74? Well, 2.74 less the mean divided by the standard error. Look it up, it's about 4%. So if I go back here, let's actually scribble that value in. 0.04 is the area in that tail. So 4% is pretty rare. It's unlikely that we would ever observe a value like 2.74 if the true mean were 2.6. This 4% is a very important number. It's called the p-value. I've stated the hypothesis for the interpretation of it for you right here. So it's called a p-value. Another name for it is observed significance. So SPSS likes to call it observed significance, or SIG for short. And here's what we do with this. Whenever p is less than 5%, we say that the result is statistically significant. Some software packages, including parts of SPSS, will put a star by the mean, indicating that it's statistically significant. Whenever p is less than 1%, it's said to be highly significant, and then you give it 2 stars. So whenever p is less than 5%, we say it's statistically significant, and we kind of rule out the null hypothesis. One more thing on these terms, statistically significant and highly significant. In a statistical context, never use the word significant unless you mean that you've done a hypothesis test and found a p-value to be less than 5%. So it's kind of a convention that the word significant indicates that you've done a hypothesis test. A lot of people use the word significant as a synonym for important, so don't do that. Here's the general procedure for testing a hypothesis. So you want to state your null and alternative, and then you gather your data. So this is the traditional scientific approach. You have a hypothesis, you state that hypothesis, then you go gather your data. You go find the p-value, and then it's really very simple. If p is less than the type 1 error rate that you're willing to live with, which is usually 5% in practice, you reject h0. If p is greater than alpha, you can't reject h0. So this is really simple. If p is less than alpha, you reject, otherwise you can't reject. Students find it kind of hard, but don't make it more difficult than it is. Now, the book talks about 2 other approaches to doing hypothesis testing, and it's good to know them. One is called the confidence interval approach. If you compute a confidence interval, and if the reference value falls inside of it, then you cannot reject the null hypothesis. If the reference value falls outside of it, then you can reject it. One more thing, whenever you report results, you should report 4 different parts of them. So first, what null and hypothesis did you test? What null and alternative hypothesis did you test? Which test did you use? So you used, say, a t-test. Give the p-value and state your conclusion. So you should always state those 4 things. Now, it turns out that there are really 2 types of tests. So the 2 types of tests are called one-sided and two-sided tests. One-sided tests involve an alternative hypothesis where there's either a greater than or a less than sign in the alternative. Two-sided tests always have a not equals, so that's all there is to it. So two-sided tests have not equal, one-sided have either a greater than or a less than. If you have no a priori knowledge that the true mean is going to be greater than 2.6, then you're better off assuming a two-sided alternative. So you'd say, I really don't know if it's bigger or less than 2.6. Therefore, I'll be conservative and allow for either tail. So let's go back to the sketchpad. And if we wanted to do a two-sided test of this problem, so H naught is that the mean is 2.6. The alternative is that mu does not equal 2.6. So if we wanted to do this two-sided test, what we would do is examine a symmetrical tail. Remember, we have no a priori knowledge that the mean is going to be definitely greater than 2.6. Therefore, we're going to consider another tail over here that also has area 4%. And the p-value is then going to be 2 times 4%, which is 8%. Now, you probably noticed that this is not significant. This is greater than 5%, so not significant. And this raises a bit of a problem. So, first off, note that the p-value for a two-sided test is always twice as large as the p-value for a one-sided test. Which one should you use? Well, the answer is it doesn't matter as long as you do what I said to do on the previous slide. So the previous slide said state what you did. So did you do a one-sided or two-sided test? And give the p-value. So if you did a one-sided test and your reader or audience thinks you should have done a two-sided test, then the reader can always multiply the p-value by 2. Conversely, if you did a two-sided test and the audience wants a one-sided test, they can cut the p-value in half. The conservative approach is to do a two-sided or two-tailed test all the time. In fact, the statistical software packages kind of lead you down that path. And so what I'm going to recommend you do is just always do a two-sided test. Let's go back to us for a second to the problem we were just talking about. So if you do two sides, you have a p-value of 8%. It's statistically significant. If you do a one-sided test, it is significant, and you would reject H naught. If you go back to the procedure for doing hypothesis testing, I say you're supposed to state the null and alternative up front. Data snooping is not allowed. Data snooping is where you look at your data and then you state the null and alternative hypothesis. So you look at the data, you'd see that it was 2.74, that's greater than 2.6, and you'd say, well, let's just have a one-sided alternative, therefore I can reject H naught. You're not really allowed to do that. That's kind of cheating. You're cheating by looking at your data first, and that's frowned upon. So you don't want to do that. All right, good. We'll now do some problems, but I'll work those in a